And also for this session is Lubin.
My name is Lubin. I'm a PhD student at the Department of Pharmacology. Thanks for the opportunity to present here my work. And what I'm going to bring to you in the next 12 minutes or so is literally entirely pain. I'm not joking. So what I'm going to talk about is the HSIN2 ion channel's role in pain. First of all, let's see a photo.
By the way,
What do you see? Walking on fire. So there are people in this world who have congenital diseases who do not sense any pain. Therefore, these people can do supernatural things like walking on fire. You might find it very cool to be able to have such a superpower to do this, but actually, in reality, people who do not experience any pain, it is a very unfortunate event for them. Sometimes even life-threatening, because pain is working as a warning system to prevent us from potential environmental damage. So the condition I just described is called congenital analgesia. So these patients, they are born to be insensitive to pain. In other words, they cannot experience any painful events. And it is possibly due to the mutations in LAMP1.8 ion channel, which is a sodium channel we will cover later, but I'm not going into the details. It is a very, very rare condition. Only 35 cases reported in the US and probably less than 100 in the world. As I mentioned, those people often suffer from overwork of joints, fractures, and breaks, and infections after injury. Actually, there are only less than 1% of patients with this condition can live to age 25, so they die really young. It's a very unfortunate event for them to not be able to sense pain. The complete opposite to this condition is those patients who constantly experience pain. I'll give an example of fibromyalgia. Those patients have persistent pain with no known cause, and it is affecting a lot of people, 5 million Americans 18 or older. Interestingly, it is affecting female more than male. The female to male incidence ratio is approximately 9 to 1. In other words, out of these patients, 90% of them are girls. It is a bit unfortunate for those, but at least we don't get bored. So there's no effective pain management for these conditions. So the point I want to make here is that the pain system is very important. It is warning us from potential damage. At the same time, we want it to be functioning normally. Either way, it will cause troubles to us. I'm sure every one of you have experienced pain in some point in your life. It can be a paper cut, it can be a hit of your funny bone, it can be migraine or tooth pain. In order to understand the pain pathway and the mechanism behind the pain, a lot of work has been done in the field. 300 years ago, 350 years ago actually, there's this guy called Rene Descartes, hope I pronounce it correctly. In his book he described the long fiber running from the foot to the cavity in the head, and when activated, release a fluid that makes the muscle contract. Of course, it's a very primitive version of the pain pathway, but actually it's already quite close to our modern understanding of how the pain pathway is arranged. So one understanding is that there are peripheral nervous system which can transduce various environmental stimulus into electrical signals, which then transmitted to dorsal cord of the spinal cord, and then via the spinal thalamus tract to thalamus and then onto the cortex to form the pain sensation. There's also an inhibitory pathway in place to modulate the whole process. I'm not going into the details about the various regions in the brain that is involved in the pain sensation, but we're going to have a detailed look in the in the peripheral part of the whole pathway. So there are nociceptors, which means the neurons that sense those various noxious stimulus to sense the stimulus and then transduce them into action potential firing and then pass them on to the dorsal horn neurons, then onto the central nervous system. There are various substances, or in other words, detectors, that is transducing those various stimulus. I'll give you an example of chip V1. So chip V1 is a heat sensor. If you put your hand on a lighter bulb, of course when it's on, or a cup of hot tea, you will feel painful and withdraw your hand. That is because this channel is detecting any temperatures above 43 degrees. Therefore, you feel painful and withdraw your hand. Interestingly, this channel can also be activated by a substance called capsaicin, which is a major substance in the pepper. That's why when you eat spicy food, you feel hot. So everything has a scientific reason behind it. Chip A1 is known for noxious cold stimuli and acids for protons, chemical noxious stimuli. So when these various detectors detect those painful events, they will transduce them into action potential firing. You can imagine action potential firing as language of neurons. So when action potential is fired, the neuron will release a neurotransmitter, which then acts on the next neuron to cause another action potential firing. So this chemical electrical communication is just like we speak in English and French, the neurons speaking this way. It's a very finely tuned system. I want to make a point here. The frequency of action potential is directly linked to whether or not or how much pain you experience. So there are various ion channels which are modulating the properties of action potential firing. Particularly sodium ion channels are a major focus nowadays because a few mutations are linked to the painless or painful phenotypes in human patients. But we are interested here is a channel called HCN ion channels. HCN here is abbreviation for hyperpolarization activated cyclonucleotide modulated ion channels. I know it's way too long, but you don't need to know the exact meaning. So it has features that can modulate the firing frequency of these neurons. Therefore, if we can develop blockers of this ion channel, we hopefully can develop new painkillers, which is different from the known two major groups of painkiller, which are anti-inflammatory, which acts on peripherally, and opiates, which acts on centrally. So that is the aim and the logic why we are interested in this ion channel, and we want to investigate the role of this ion channel in pain pathway. And I just give you an example how this ion channel is modulating the firing frequency of the excitable cells. I'm now using a cardiac myocytes as an example. So at the end of action potential, you reach hyperpolarization, which activates HCN channels, which generate inward current, push the threshold back to the firing threshold and fire another action potential. In the event of cyclic AMP modulation, let's give an example. For example, you seeing a beautiful young sexy lady walking into the room, or you are watching the penalty kick of the Champions League final. You have an injection of adrenaline in your circulation system that will lift to the cyclic AMP level, which then enhance the activity of HCN channels, which means that you will have a faster and more HCN current, which the result is to increase the firing frequency. So this is the model in the cardiac cells. However, we see the same modulation effect is happening in the nervous system. What we do is we generate HCN2 knockout mice. In other words, these mice do not have HCN2 ion channel. Indeed, we found that in nociceptors, if you add phosphine, which is irritant, the neurons will firing action potential spontaneously. But when you knock out HCM2, in the same group of neurons, there's no spontaneous action potential firing at all. And phosphine can also increase the firing frequency of those neurons, but such an increase is not observed when you knock out HCM2. So the point I want to make here is HCM2 is critical in modulating not only the spontaneous firing of these neurons, but also the firing frequency. So they are directly linked to how much pain you experience. So we want to move on to the animal behavior work, generating these HCM2 knockout mice and observe whether they have any changes in their behavior tests in pain models. However, those HCM2 knockout mice, they have very severe phenotype. They suffer from epilepsy. They also do not survive usually about 4 weeks. So I can see some of you, which I'm going to be quick about this. So we want to generate a conditional knockout mice, which means that we only knock out HCM2 not in every neuron, but only in a subset of neurons, which is driven by the NaV1.8, which we know is only expressed in nociceptors. In other words, we only knock out HCM2 in nociceptors, as you can observe here. So this is the NaV1.8 expression. In the wild type, HCM2 is expressed in about 30% of the neurons, which is not shown here. But when you knock it out in the NaV1.8 neurons, you can only see sparsely 2%. So the majority of them is knocked out. What is the effect? What we did is we basically put a little knot on the sciatic nerve of the mice. So after the surgery, the mice will develop neuropathic pain, shown by the reduce of time threshold when applied heat or mechanical stimulus. And we found that in the mice which have HCM2 knockout in the nociceptors, such reduction is not observed anymore. In other words, if you knock out HCM2 in the nociceptors, those mice cannot develop neuropathic pain. In conclusion, HCM2 is very important in the development and maintenance of neuropathic pain. We also wanted to figure out why this channel is mediating the hypersensitivity of the nociceptors, and we suggest that in both DRG neurons and in nerve endings, these channels' expression level will increase after the nerve injury. Therefore, leads to the increased HCM current and the increased excitability of the neurons, and then leads to more pain. Basically, that's the logic. In conclusion, we confirmed that HCM2 ion channel plays a central role in both inflammatory and neuropathic pain. And this is the first transgenic study that showing the knockout of an ion channel is capable of abolishing neuropathic pain completely. Therefore, HCM2 can be a target for developing neuroanalgesics in the future.